Hi everyone, this is Dr. Amsaveni, Associate Professor PG and Research Department of Mathematics, Sri Sharada College for Women, Salem. In this video, we shall discuss the norm-linear space, some results on norm-linear space, and finally norm on quotient space. So we know about the vector space. If we have the space which is said to be vector space, then it satisfies 10 axioms. 5 axioms related to addition and rest of the axioms related to scalar. This is we know. So in the same way we can define the norm-linear space. If we say that the space is norm-linear space, then it satisfies some axioms. So we know about the norm of the vector, that if we have uh, the vector and we find the norm of the vector represented by double bars, and the answer will be the scalar, that is a real number, the length of the vector. Therefore, the norm is the length of the vector, the length is a real number. So we can say that the norm is a function that takes a vector as an input and gives a scalar as output. Therefore, we have a function from a linear space to scalars. So we can define the norm linear space as follows. So a norm on a linear space is a function which is denoted by double bars. So it is from n to r. Here n is a linear space over the field f that may be real or complex. Then the function must satisfy the following axioms. The first axiom is, if we take any element x from the linear space n, then the norm of the element x must be positive or it is 0. It cannot be negative by the definition of length. That is, the length of the vector must be positive or 0. So therefore, for all x belongs to n, norm x greater than or equal to 0. The next one is, if we have the vector in the space n whose norm is 0, then the element x is also 0. That is, norm x is equal to 0 if and only if x is equal to 0. So therefore, if we take an element from n is 0, then we say that the vector is 0. So this is also true in the converse, that if any element is 0, then its norm of the vector is also 0. The third axiom is, if we have a sum of two elements from the space n and the norm of these element from n is less than the norm of x plus norm of y, here we use the triangular inequality. And the fourth axiom is, if we have a scalar alpha and an element of n is x, and we take a norm of the scalar multiplication, then this norm of the scalar must be equal to the magnitude of the scalar, because the scalar can be negative, and this is the reason to take the magnitude of the scalar. So therefore, the last axiom is norm alpha x is equal to modulus of alpha into norm x. If the function norm satisfies these properties, then we can say that the pair of norm with the space n is said to be norm linear space, or simply a norm space. Next, we have a discussion on the relation of metric and a norm linear space. So we know that the metric space is about the distance among its elements, and the relation between the norm space and the metric space is, every norm linear space is a metric space. So next we are going to see the proof of this statement. To prove this, we have a function d such that d from n cross n to R is defined by d of xy is equal to norm x minus y, where xy taken from the linear space n. To prove this relation, we have to show the basic three properties of metric space. The first is non-negativity, d of x comma xy is greater than or equal to 0. The second one is symmetry, d of xy is equal to d of yx. Third one is triangular inequality, d of xz is less than or equal to d of xy plus d of yz. Then talking about the first property, the metric should be greater than or equal to 0. So by the definition of the norm x minus y, it should be positive. That is, norm x minus y, the length of this element must be positive. By the definition of norm, we can say that norm x minus y is greater than or equal to 0. So therefore, d of xy greater than or equal to 0. But if d of xy greater than or equal to 0, then norm x minus y is equal to 0. Again, by using the property of the norm, if the norm of the element is equal to 0, then the element is equal to 0. So therefore, norm of x minus y is 0 if and only if x minus y is 0. So this implies x is equal to y. Therefore, the function d must be positive, and if the function d is 0, then the distance between two elements are same. The second property is about the symmetry. In the function, we defined d of xy is equal to norm x minus y. So taking minus sign from this, then we get norm minus y minus x. And then, so we know that norm a modulus the absolute value of a is a if a is positive. Modulus of a minus a is also a if a is negative. So this case we are going to consider here. So therefore, the norm of the negative of y minus x is norm y minus x, and by the definition it is d of yx. So moving to the third property, so if we write d of xz is equal to norm x minus z for triangular inequality, so we have to take three elements from the norm linear space. Say x, y, z, it's from n. Now we apply the function beyond x and z, so we will use x, y and y, z. Now d of x z is equal to norm x minus z. So this is norm x minus y plus y minus z. This is less than or equal to. So we can here we can form a pair of x, y and y, z, y minus z, x minus y and y minus z. Since there is a symmetry in it, and norm x minus y plus norm y minus z, and we can write it is less than or equal to norm x minus y plus norm y minus z by using the triangular inequality of the norm space. Therefore d of x z is less than or equal to, so this is by the definition d of xy plus this is d of yz. Therefore we have proved d of xz less than or equal to d of xy plus d of yz. Therefore d on xz must be less than d of xy plus d of yz. And finally d of xx is equal to norm x minus x, which is 0. Therefore all the properties of a metric are satisfied here. Therefore we proved every norm linear space is a metric space. The next result, for all xy from the linear space n, we have modulus of norm x minus norm y is less than or equal to norm x minus y. So let us see the proof. So we consider norm x. Norm x, we can write this x as x minus y plus y. Add and subtract y. This is less than or equal to norm x minus y plus norm y. And norm x, so take this norm y to this side, and this will be norm x minus norm y, which is less than or equal to norm x minus y. Similarly, we have norm y is less than or equal to norm y minus x plus norm x. And this norm x will be minus norm x in this side plus norm y less than or equal to x minus y. Norm x minus norm y multiplied by minus sign here. Minus norm x minus norm y is greater than or equal to minus norm x minus y. So minus norm x, this implies minus norm x minus y is less than or equal to norm x minus norm y. So combining 1 and 2, we get minus norm x minus y less than or equal to norm x minus norm y less than or equal to norm x minus y. So we know that minus delta less than or equal to x less than or equal to delta. That implies modulus of x less than delta. So therefore from this inequality we have modulus of norm x minus norm y is less than or equal to norm x minus y. The third result is norm is a continuous function. That is, whenever xn tends to x, norm xn tends to x. So we know that the continuous function definition. So if any sequence xn converges to x, that implies f of xn tends to f of x, then we say that f is continuous at x. So let us see the proof. Suppose xn converges to x as n tends to infinity. This implies xn minus x tends to 0 as n tends to infinity. And then this implies norm xn minus x converges to 0 as n tends to infinity. By the result 2, modulus of norm xn minus x is less than or equal to, the result 2 is modulus of norm x minus norm y is less than or equal to norm x minus y. So norm xn minus norm x less than or equal to norm xn minus x. This tends to 0 as n tends to infinity. Therefore, so this is tends to 0 as n tends to infinity. So from this, norm xn tends to norm x as n tends to infinity. So whenever xn converges to x and norm xn approaches norm x, therefore we can say that this function norm the function norm is a continuous function. So the next result, the addition and scalar multiplication are jointly continuous. So here we prove whenever xn approaches x and yn approaches y, then xn plus yn approaches x plus y. The second, whenever alpha n approaches alpha and xn approaches x, then alpha n xn approaches alpha x. Let us see the proof. Given xn converges to x, this implies norm xn minus x converges to 0 as n tends to infinity. Similarly, yn converges to y implies norm yn minus y converges to 0 as n tends to infinity. Now consider norm xn plus yn minus x plus y, which is equal to, we can form a pair like this, xn minus x plus yn minus y from this. So this is less than or equal to norm xn minus x plus norm yn minus y. This is converges to 0 as n tends to infinity, because this is tends to 0 as n tends to infinity. Norm yn minus y is also tends to 0 as n tends to infinity. Therefore, norm xn minus x plus yn minus y converges to 0 as n tends to infinity. And hence norm xn plus yn minus x plus y approaches 0 as n tends to infinity. So from this, xn plus yn minus converges to x plus y as n tends to infinity. Therefore, addition and scalar multiplication are jointly continuous. The next one is alpha n tends to alpha, modulus of alpha n minus alpha tends to 0 as n tends to infinity. To prove norm alpha n xn minus alpha x tends to 0 as n tends to infinity. So we consider norm alpha n xn minus alpha x plus alpha n x minus alpha n x. See here, we are adding alpha n x and subtracting alpha n x here. So therefore, which implies now alpha n can be taken outside, so xn minus x. So from these two terms, alpha n can be taken outside, so xn minus x. From this we can take x outside, we have alpha n minus alpha. This is less than or equal to, by the definition of norm linear space, so it will be modulus of alpha n into norm xn minus x. Here also the scalar is alpha n minus alpha, so modulus of alpha n minus alpha to norm x. This converges to 0 as n tends to infinity. Since norm of xn minus x and modulus of alpha n approaches 0, therefore these two terms approaches 0 as n tends to infinity. Hence alpha n xn approaches alpha x. Next, let us see the norm on a quotient space. So before that, let us see what is quotient space. So if we have a norm space n and a subspace of n is represented by m, any element of the norm space that may be inside m or outside m. Then for any element of a norm space n, and we form a set by adding x plus m, which is the set and the element is of the form x plus m, where m is an element of m. This set is called a coset of M determined by X, and the set X plus M where X belongs to N of all the cosets of M is a linear space under addition and scalar multiplication. So, linear space means it satisfies two basic properties, addition and scalar multiplication. That is, if we have two elements X and Y belongs to N and alpha belongs to F, then the sum X plus Y and alpha X, the scalar multiplication, which is also in N. Similarly, if we take cosets X plus M and Y plus M from the quotient space N by M, then the addition X plus M plus Y plus M is equal to X plus Y plus M. X and Y are the elements of N. Also, the scalar multiplication alpha times X plus M is alpha X plus alpha X plus alpha M. So, this is just M. So, therefore, alpha X plus M. Here X is the element of N and alpha is a scalar which belongs to F. So, this set of cosets of M in N is called the quotient space of N by M, which is denoted by N by M. Based on this quotient space, we have one theorem. Next, we are going to prove if the norm of a coset in the quotient space N by M is defined by norm X plus M is infimum of norm X plus M, then norm N by M is the quotient space N by M is a norm linear space. So, we need to prove. So, to prove N by M is a norm linear space, we need to prove the four properties of the norm linear space. The first one is norm X greater than or equal to 0, norm X is equal to 0 if and only if X is equal to 0, and norm of X plus Y is less than or equal to norm X plus norm Y, and finally norm alpha X is equal to modulus of alpha into norm X. So, let us prove the first property of the norm linear space, that is norm X greater than or equal to 0. Here we have norm X plus M. So, we need to prove norm X plus M is greater than or equal to 0. So, let us take the element X plus M in the quotient space N by M, and by the definition norm X plus M is infimum of norm X plus M. So, to prove norm X plus M is greater than or equal to 0. So, we know that norm X plus M, the length of this vector, the length of this element is a positive real number. So, this is a positive, since this is a positive real number, so we have infimum norm X plus M is also a positive real number. So, therefore, norm X plus M is greater than or equal to 0. To prove the second property, norm X plus M is equal to 0 if and only if X plus M is equal to M. So, that is the 0 element in N by M. Suppose, so we take norm X plus M is 0. So, by the definition it implies infimum of norm X plus M where M belongs to M. So, this is also 0. So, that by the property of infimum there exists a sequence Mk in M such that norm X plus Mk tends to 0 as k tends to infinity. Then X plus Mk tends to 0 as k tends to infinity. This implies Mk tends to minus x as k tends to infinity. So, we know that M is a closed subspace. So, therefore, minus x, the element minus x is also belongs to the closed subspace M. So, x belongs to M. which implies by the property of coset, if x belongs to M, then x plus M is equal to M. So here we have x belongs to M. So it can be written as x plus M is equal to M. That is the zero element in the quotient space n by M. Therefore, norm x plus M is equal to 0 if and only if x plus M is equal to M. That is the second property, norm x is equal to 0 if and only if x is equal to 0. So the norm of the element x is 0, then the element is also 0. So here similarly norm x plus m is 0 if the element is also 0. That is the 0 element in the quotient space n by n. To prove the third property, so that is the triangular property, triangular inequality. So let us take the two elements x plus m and y plus m in the quotient space n by n. Here these are the elements from n, and consider norm x plus m plus y plus m, which is equal to, so we can write norm x plus y plus m, and by the definition it can be written as infimum of norm x plus y plus m, where m belongs to m. And in the next step we consider m as m1 plus m2. So therefore infimum of norm x plus y, this m will be m1 plus m2, where m1 m2 it belongs to m. And we can form a pair like this, infimum of norm x plus m1 and norm y plus m2, norm of x plus m1 plus y plus m2, and this is less than or equal to infimum of norm x plus m1 where m1 belongs to m, and infimum of norm y plus m2 where m2 belongs to m. And again by the definition, so this term can be written as norm x plus m, and this will be written as norm y plus m. So therefore norm x plus m plus norm y plus m is less than or equal to norm x plus m plus y plus m. Thus we have proved the third property. Finally, the fourth property, scalar multiplication. So for an any scalar alpha and the coset x plus m in the quotient space n by m, consider the element alpha x plus m, alpha x plus m. Alpha x plus m is equal to alpha x plus m. So if alpha is 0, then we have the 0 element in n by m. Since norm 0 into x plus m is equal to 0x plus m, so which is norm m. So this is the 0 element in the quotient space n by m. So let us consider alpha is not equal to 0. Then we prove that norm of alpha into x plus m is equal to modulus of alpha into norm x plus m. So consider norm alpha into x plus m, which we can write alpha x plus m is equal to, by the definition, infimum of norm alpha x plus m, where m belongs to m, and this will be infimum of norm alpha into x plus m, and we can write infimum of modulus of alpha into norm x plus m, where m belongs to m. So modulus of alpha into infimum of norm x plus m, where m belongs to m. So modulus of alpha, so this we can write it as norm x plus m. So therefore we have proved norm alpha into x plus m is equal to modulus of alpha into norm x plus m. So we have proved all the four properties. Then we have shown that the quotient space n by m is a norm linear space.